I knew I had reached a good phase of my career when a free t-shirt was no longer an incentive. I was like, I don't know. Okay, let's see. Today we're going to wrap up some of this organic chemistry review and chemistry principles, and then Friday we're going to move into electrostatic interactions and Coulomb forces. So we're, I think, delayed like one day relative to the schedule. So we'll see how the rest of it goes. So for Friday, though, do read that chapter 10 or start working on it. Okay. There is a homework on TED. Homework number 1 is posted, and then it'll be due a week from today. Yes, start reading. Oh, and I sent out an email that my office hour, I hate to be a moving target, but this week it's Friday 1 to 3 instead of Thursday 1 to 3. Okay? Any questions about that? Okay, so an unresolved question from last week was why does lanthanum go into 5d1 before start filling the 6s, or I'm sorry, the 4f orbital? And you know, the short answer is that it has lower energy. Okay. The longer answer is to think a little bit more about how the energy levels are arranged. And so as you go up in the principal quantum number, right, you get higher and higher principal quantum numbers. The energy, of course, gets higher, but the differences between those energy levels becomes less extreme. Okay? So the difference between a 1s and a 2s is big. The difference between a 2s and a 3s is big. But the difference between a 2s and a 2p is relatively small. Okay? And so that's why we filled, and the difference between a 4s and a 4p is small, but the difference between a 3d and a 4s is also small. And that kind of makes sense when you think about the shape of these orbitals, right? So if you think about the distance from the nucleus of something like a d orbital or an f orbital, these are on balance much farther from the nucleus, so they have higher energy. Okay? So extending that logic up, when you look at the difference between a 5d and a 4f, they are not very different in energy. Okay? So that's one part of the answer. The other part of the answer is how happy are, and I hate to make electrons anthropomorphic, but I don't know any other way to do it, is to, let's take an example like chromium. Chromium and copper are two really common examples. So chromium would be this, right? Argon, and then 4s2, 3d4, right? You can do this in your sleep. Okay, so what that really looks like is this. Okay. It turns out that this is not happy, right? This configuration, having this orbital unoccupied, this is what you would think. What actually happens is that one of these 4s orbitals moves over here. This is for chromium. To fill this entire orbital halfway is more energetically favored than this situation. Right? This is what you would predict. Yeah?
So would that be a better contrast agent for MRI than manganese?
Yeah, would this be a better contrast agent for MRI than manganese? No, because this is it's going to be in resonance, and manganese is going to be forced to stay in that position. Okay. So let's look at another kind of example. Let's look at copper. So copper would be 3d9. So this is what it, if you just were to write it as it's written on the periodic table, right? But what copper actually ends up doing is, again, moving a 4s over, so the 3d is completely filled. And so it has a 3d10 configuration for S1. Yes?
Is there a reason why that's more favorable to complete the 3D over the 4S?
Because there are more orbitals and they're farther away from the nucleus. So that's, if those are filled, the overall energy of that orbital is lower. Yeah.
How does that make sense when we're writing like molecular orbital diagrams when the 3D is above the 4s in energy level? So it's actually like, it doesn't make sense like computationally when you're calculating energy levels if it's jumping up rather than does it happen?
Why does it happen? Because to have this 40% full or 90% full is particularly disfavored. So, I mean, don't think of this as being locked in stone, right? These can move up and down relative to how many electrons are in them. Yeah.
By the same logic, the silver and gold also follow the same principle?
Yeah, yes. Yeah, generally these trends are going to follow all the way down the column. Yes.
Is that why we see copper, silver, and gold as such good conductors? Because they have the isolated s electron?
I don't know. I mean, the reason they're good conductors is because they have delocalized electrons. I don't know if it's a function of having that one in the 4s particularly unpaired. Yeah.
Just another question.
Yes.
Given this, when you're supposed to write the configuration, are we supposed to do like 4s1 and 3d10 instead of?
That would be correct. You know, I was kind of just getting into this to go to as more of a subtle detail. I don't think I would ask you for the exceptions to the rule explicitly. Yeah. Yeah.
I was just going to ask if these were like the exceptions that we talk about in general chemistry.
These are some of the exceptions. Yeah. Yeah.
Why is gold so much more inert than copper?
Because even though the valence configuration is the same, it has more inner shell electrons, right? So the proportion of reactive electrons is lower. Okay, yeah.
So is gadolinium the only F orbital that follows the same exception?
No. So then getting back down to the lanthanides, we see something very similar. So europium. So europium, where would we be here? We would be xenon. Xenon, and then 6s2. If you were just to write it as you would expect, that would be 5d1, and then 1, 2, 3, 4, 5, 6. 4f6. But what this also tends to do is that tends to hop over here to make that a half full shell for europium.
Why does only one of the D get filled? So, like, that doesn't like intuitively make any sense to me. Like, wouldn't it want to fill the D?
Nope, because the energy levels are very, very similar, and so this is more energetically favored to have this entire f orbital half filled than this one half filled.
So there's no D for.
Nope, nope. That's a more likely resonance structure of europium. Yeah.
So I guess the original point of bringing up this stuff was the question last time.
Why does it drop into 5D first?
Looking at, yes.
Yeah. So doesn't that make sense if you had D versus an F? If you were to only have one electron there, these are smaller orbitals. There are fewer orbitals. So that's why the D will go into there. If it has to be all on its own in a D orbital, it's lower energy than in an F.
But if we added one more electron, say at cerium on the 58, then we would see one in the D and one in the F.
What is cerium? So, you know, there are tables 4F1 so lanthanum and then cerium. So this, yes, it does drop into 4F1. Yep.
Do structures like ever oscillate between two configurations? Or?
Yeah. In terms in heat, in yeah. It's appropriate to think of it as somewhat in resonance. Yeah. Yeah. Okay. You also get that this is not the same as oxidation state, right? Because gadolinium is 3+ generally, right? And that's because the electrons are paired to the protons, and that's what causes oxidation state. Okay. So I have these. This is another one I stole from the web that plots the valence electrons. If you're interested to some of these exceptions. But the bottom line of why 4D is that there's more orbitals, and to have this is better than having one in the 4F, where you've all these different options farther away from the nucleus. Okay. Okay. So that's atoms. So now what about molecules? We know the octet rule, right? That atoms tend to wiggle around in order to arrange to somehow get a configuration to make them look like a noble gas, right? And that can be either through an ionic bond, like we see in quantum dots, where it's a transfer of electrons, or a covalent bond, like is in carbon nanotubes, where it's a sharing of electrons. Okay? So how to understand how these electrons are configured. So it's important to know how to draw these Lewis dot structures, and I think when we did the poll, most people were somewhat familiar, but I want to refresh this to do some of these. So the steps to drawing a Lewis dot structure, so you understand how many unpaired electrons a species has and where those electrons are located. This is, despite being kind of a rudimentary tool, is still pretty powerful, because that will then go on and govern its electronegativity, which will govern its reactivity. Okay? So let's do something. Let's do water first. Water's easy. So step one in drawing a Lewis dot structure is add up the number of valence electrons. So how many valence electrons do you have for oxygen? 6, right? Because it's in group 6. How many for hydrogen? 1. So 1 times 2 plus 6, you have 8 electrons. Okay. So how many electrons does each atom want? How many does oxygen want? 8. How many does hydrogen want? 2. Yeah, 1, because it's going to be a shared pair, right? How many bonds can oxygen have? Generally, it has 2, right? And hydrogen then has 1, right? So actually, let's draw it more simple. So there's 2 electrons that are shared. 4. The remaining, so we've got 4, we have 4 left. Oxygen wants 8. So that's what the Lewis dot structure of water would look like. Now you can go back and count your formal charge. How much charge is on each atom? And of course, you know that this looks like this. If we draw a line like that, that this represents a pair of shared electrons. So the charge on oxygen, it starts with 6, and it has, and then we're going to subtract the 4 that it has on its own plus 1/2 of the 4 that it's sharing. So 6 minus 6 equals 0. So there's no charge on the oxygen, right? Nor is there a charge on the hydrogen. Okay? So what would this look like if we did H2S, dihydrogen sulfide?
The same.
It would look exactly the same, right? Because we're only dealing with valence electrons, right? So the fact that it's got all this other junk in a lower, well, it's not junk, those are pretty important orbitals. It's got all these other orbitals below the 3p orbitals. The 3p is what's doing the business, right? So that's why it looks like that. Okay? What about carbon tetrachloride, CCl4? Can do that one really quickly. Chlorine has 7 times 4 plus the 4 from carbon. Right? So carbon's going to be your center. Right? Yes?
Do you expect us to include stereochemistry?
Probably not. You can do it though. Yeah. Okay. So here's a good cheat sheet in terms of, and this is from your reading, what most of your organic centers want to, are happiest in. So here the valence is the, we're not talking about necessarily, it's related, right? It's how many bonds an atom usually forms. That's what they mean here by valence. This isn't the number of valence electrons that it has available, right? Valence has a different word on this chart. And you can think about that, remember from Aaron Brockovich when they're talking about hexavalent chromium, right? So that is how many bonds it tend to form. Carbon is tetravalent, right? So have this kind of stuff should be tattooed in your brain, right? Like if you ever draw something like this, like that should make you cringe, unless you have a charge on it, right? Okay. Could you do phosphate? About number 5.
Phosphate is 5 and oxygen has 4 by 6,
So how many do you have to work with?
you have 29 minus the 3 charge.
Not minus.
So add the 3 might be.
Yeah. So you've got PO4, 3 minus. So phosphorus has 5 plus 4 times 6 plus you have 3 extra from your electron. 4 is 24 equals 32 to work with. So let's just draw it like this. Okay, so our central atom. So then we start, okay, so we've used up 2, 4, 6, 8. So you might want to go 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So is this, what do you think about this? So what would be the charge on this? So for on each oxygen it would be negative, and phos would be +1. But what actually happens is that you get a double bond on one of them. And that's your 3-, and phosphorus has no net charge.
So you want to make it so your central atom doesn't have a net charge?
That's generally more stable. Yeah.
What is that? The phosphorus would exceed 5%?
Say that again?
So for the other resonance structure?
Yeah.
Doesn't that have, the phosphorus has 10 electrons in it?
On these, if it's a shared set, so you're right, this is 2, 4, 6, 8, 10 electrons, but when it's shared, you only count them as half when you go back and count the neutral charge. So on my instruction, so to count the electrons afterwards to determine charge, if it's a shared pair, it counts as only 1, right? So it originally had 5, and then you've got 1, 2, 3, or 2, 4, 6, 8, 10, but they're only counted as half because they're shared. So 5 minus 5 is 0.
My question is, why would the one at the bottom be more stable than the one from the top? Because the bottom one has 10 electrons and the top one only has 8.
It's not, it doesn't have 10 electrons per se. And here you have every atom has a charge, right? Whereas here, only 3 atoms have a charge. This one, and this one. So to have every atom charged or have a difference from its valence state is uncomfortable relative to only having 3, right? Yeah.
So is your last table equals 4 double bonds?
To have 4 double bonds. Oh, well, yeah, okay, so what would that look like? P. I don't even know what that would look like. 2, 4, 6, 8. 4 times 8 is 32, so that's the right amount of electrons. So then here you have why can't you do this? This is a weird structure. Because phosphorus would never do this is the short answer. Because there's not enough room to accommodate that many shared pairs of electrons at phosphorus. So you would not do that. You would not do this. This is what it's more stable. You guys have not had organic, right?
Also, for the
Yeah.
4 double bonds, isn't it then not even charged?
No, because then the phosphorus would have 5 minus 2, 4, 6, 8. Minus 8 is, yeah. So you would still have, the charge balance still works.
But it's just all on the center atom.
It's all on the center atom, yeah. Yeah.
So for our actual resonance structure that we would see, the one at the bottom right?
Yes.
We would see that in resonance where the different oxygens would sort of...
Exactly. Yeah, exactly. It's not, and in fact, all of these are perfectly equivalent, right? Even from a stereochemistry perspective. I mean, what that really looks like is, and then this one. So if you see me draw something like this dashed triangle, that means it's coming out of the board. And if you, well, a solid dashed triangle, and if it's a hatched dashed triangle, that means it's going into the board. Okay, these two are in plane, and then this is coming out, that's going in. Yeah.
Do we need to know all the stereochemistry?
No, I'm not going to ask you stereochemistry for sure. But hopefully, this is hard to get without a model. I don't think I have a organic chemistry set anymore. But if you see this is a tetrahedron, all of these are perfectly equivalent, like if you rotate it. The other example that you see a lot is carbon tetrachloride that I drew at first. I'll see if I can find one, because when you rotate it, they're completely the same in every way. So his question, going back to the original question, was, is this one like a unique? And it's not, because these can be in resonance with each other. You could just as easily write this as yeah, right? This is the same. Okay. Anything else on phosphate? Okay. What about ethylamine? Actually, to be fun, let's do propylamine. Could you do the Lewis dot structure of that? Try it.
Professor, I think it's one propylamine.
Yeah. So do the full Lewis dot structure.